Hello there! During the past two videos, we have looked at the subatomic particles and electrons in particular. We noticed that atoms aim for a state where their valence shell is full, and these atoms with a full valence shell were stable, while atoms that were close to getting their full valence shell were very reactive. Now this video will focus on various approaches how atoms may end up filling their valence shell, and in this process forming bonds with other atoms. So let's make a start on this consideration. So while we are talking about a few different things during the rest of the material on this chapter, this section is really a very important one. I want that you are all comfortable with understanding these three kinds of bonds between atoms. And let's start with covalent bonds. So when I think of covalent bonds, this is always how I remember them. Here you can see two bunnies sharing a piece of, I think it is grass that they are both eating. And the sharing is the key word here. When I talk about covalent bonds, I always say in my mind, sharing is caring. Really, that is just an example, and any trick that helps you to remember is a way to go. This just happens to work for me. So let's look at this a little more. In covalent bonds, atoms end up sharing some of their electrons so that everyone involved ends up with a full valence shell. So to use the analogy that I applied in the last video, so that everyone involved gets to their happy place. And I have a few examples of this to share with you. Let's look at those. So what I have here in this example is a starting point where we have two atoms. And let's call them, say, hydrogen atoms, just for the sake of ease. And both of these have only one electron on their outer shell. So they are not in their happy place, if you wish. For them to be there, they would both need to have two electrons on their first shell. Remember, the first shell could only fit in two electrons, right? And we also have one atom that has 6 electrons on its second shell. We remember, in order to have second shell with the electrons there, the first shell had to be filled first. So there is going to be 2 electrons there. But they are not shown in the diagram for the sake of clarity. Only the second shell with its 6 electrons are shown. And let's call this atom an oxygen atom. For this oxygen atom to reach a full valence shell, it would need 8 electrons there. So, while oxygen atom in this example needs 2 more electrons, both the hydrogen atoms need 1 more electron each. Then everyone would be happy. But hydrogen atoms simply cannot give away their current electrons. That's not possible. So what do we do instead is we do just what those bunnies were doing. They were sharing. So let's look at this a little bit more carefully. Well, now the first hydrogen has 1 electron on its own and it shares 1 with the oxygen atom. So hydrogen does not get to own the shared electron all the time, but every now and then that electron travels to its valence shell and does a full circle there before returning to the oxygen atom where it does a full circle on its valence shell. So some of the time hydrogen has 2 electrons on its valence shell and it is happy. So hydrogen atom that's That's the motivation for forming a covalent bond with the oxygen. It is a happy at least some of the time, and darn close to happiness the rest of the time. So this is a smart strategy for this hydrogen atom, right? And the same applies to the second hydrogen atom. Now, something interesting happens. By sharing 2 electrons, oxygen atoms that we have here, it gets at times 8 electrons on its valence shell. So at times it reaches its happy place. And it needed actually 2 hydrogen atoms to work with this, to achieve this. And the rest of the time, this oxygen atom is again darn close to a full valence shell. So really, if you think about this slogan, sharing is caring, kind of makes sense here. Everyone is happy. And even though everyone is not happy all the time, because these electrons have to be shared, everyone is happy some of the time. And I think it's a rather good accomplishment. And then there is another interesting thing that we will notice here. And let's look at the recording these atoms. A new molecule is now formed. Let's focus on that a little. So what I have done here is that I have faded a lot of those things that we were looking at earlier. But they are there, just not something that I wish to highlight. Now you will notice that I left the letter symbols for the elements visible. So 2 hydrogens and 1 oxygen atom. And I also left the shared electrons symbolized by these lines visible. This is going to be useful for us. And this is how we normally draw a structural formula. So when you have a single line in a structural formula, that means that for each single line, a pair of electrons is shared. I have another example for us. Let's have a look at that. So here we have 2 atoms. Both of them have on their second shell, which is also their valence shell, 6 electrons each. And remember that there is going to be full first shell, which fitted 2 electrons, but we are not just drawing it out here. So both of these atoms need 2 more electrons in order to be happy. Or in other words, in order to reach a full valence shell of 8 electrons on it, each of these atoms is 2 electrons short. Well, what can we do to help this situation? There are no single electrons available around, as we see. But not all hope is lost, not even by a long shot. What we can do is that these 2 atoms come together, and each of them shares 2 electrons with the other one. In this way, although not happy all the time, each of these atoms gets a spin where it has 8 electrons on valence shell. And then those shared electrons jump for the other atom to have its turn to hold them for 1 round. And then again and again. So this way, both of these atoms are happy most of the time and real close of being happy for the remaining of the time. And let's do what we did before. Let's draw lines over each pair of shared electrons. So we have here 1 electron pair that is shared. And here we have another electron pair. So this gives 8 electrons on each atom's valence shell, at least most of the time. And again, let's think of what our typical structural formula would look like. Yes, it looks like very much of what we are used to seeing in structural formulas. So in this case, rather than just sharing 1 pair of electrons, we have shared 2 pairs of electrons. I hope that this makes sense. I do want to throw in one more concept, and actually to review it, we can use this very example that we are looking at. Here, these electrons that are shared may be 1 or 2 pairs, as in this example. They are shared equally. Both of these atoms get to keep the shared electrons as a long time. So the sharing of these is fair, or even if you wish. This is known as nonpolar bond. But sometimes this is not the case, as we saw with this example. Here, electrons are not shared equally. In fact, in this example, the shared electrons spend more time with oxygen than with hydrogen atoms. So we can say, for an example, I cannot remember the real ratio, but just as an example, let's pick one from the thin air. Let's say that for every 1 spin of the shared electrons that the hydrogen atom gets, the oxygen atom gets to do 2 spins. So the oxygen atom is a bit greedy. And this is uneven sharing of the electrons, which means that we have a polar covalent bond. A good sign of this, usually when the structural formula, like the one that we see here, is viewed, is that it's not a straight line in terms of how each of the atoms are aligned in relation to each other, but there is a kink of some kind. It is an indication that there is an uneven sharing of the shared electrons. So the molecule is a polar one. We have now polar covalent bond or bonds. And actually, we will talk more about this very example, which is of course the structural formula for water, a little bit later, as water has some other interesting characteristics. But that was all that there was to covalent bonds for now. So sharing electrons. Let's have a look at another kind of a bond. And this time we have something called an ionic bond. In an ionic bond, we saw something that we have actually seen even earlier on in one of our earlier videos. Here, an atom either gets some more electrons or gives away some. And this was gaining or losing of an electron or electrons. That's the permanent thing. It's not just a temporary moment as earlier. Let's have a look at more of this. So, ionic bond refers to the complete transfer of valence shell electrons between 2 atoms. And this has some further consequences, which we will look at in a moment. But let's first see this concept with an example. So let's look at this initial situation. Here we have a sodium atom, and its atomic symbol is of course Na. Sodium has a total of 11 electrons. We can see this from the periodic table, where sodium has the atomic number of 11. Note that the atomic number was really the number of protons. But as this is an electrically neutral atom, it has the same number of electrons and protons. Back to the number of electrons. So if there is a total of 11 of those in a sodium, let's go through how many are on each cell. Remember that the innermost shell, our first shell, could only hold 2 of these. Then the next cell could fit 8. Well, this gets us to 10 electrons, right? So the outermost, our third shell, has 1 electron. Because sodium has only one electron on its valence shell, it will be very reactive and actively trying to get rid of it so that it can reach its happy place. Let's have a look at chlorine using the same logic. And we have here its information from the periodic table. So the atomic number is 17. So 17 protons, which in electrically neutral atom meant that there was also 17 electrons. And let's go through their locations. First shell will have 2. This is the maximum number that can fit in there. And the second shell will have 8. Again, the maximum number that can fit in there. So the third and therefore our valence shell must have 7 electrons. And we remember that we always wanted a full valence shell. In this case, it would be that the third shell would need 1 more electron. So this chlorine here would be very reactive, actively pursuing gaining 1 more electron, right? So what do we do to make everyone happy? This is going to be probably a very obvious one, but before we solve this, I just wanted to remove all other information and leave simply the number of electrons up. What we do is, of course, sodium giving 1 of its electrons to the chlorine. Everyone will be happy. So let's have a look at what happens as a result of this. And to do that, I am going to set up the original view for the left side of the screen. And now you see on the right side of the screen that sodium has gotten rid of 1 of its electrons. And as a result, it now has 8 electrons on its second shell. So it is in its happy state, right? And we also see that chlorine has received 1 electron, and by receiving it, chlorine is now able to complete its third shell, having 8 electrons on it. So again, chlorine is happy. So we have completed the first part of our definition for the ionic bond, right? But that's not all of the definition. Let's have a look at the remaining part. So based on this definition, the process of formation of an ionic bond results in atoms that are now overall differently charged. Remember our concept of electrically neutral atom. Well, these atoms are no longer neutral. Let's have a look at why. By giving away 1 of its electrons, sodium has now become slightly positive. There are still 11 protons on its nucleus, but only 10 electrons on its shell. So as we remember that protons were positively charged and electrons negatively charged, we have more pluses than minuses. This means that the overall charge of the sodium is now slightly positive. And the same applies to chlorine. Chlorine had initially 17 electrons and 17 protons. Now that it has gained 1 more electron, it has 18 electrons and it still has 17 protons. As a result, the number of minuses is greater than the number of pluses. So overall, chlorine is now slightly negative. Well, this has some consequences which we must note. Remember the old wisdom that opposites attract each other. I could think of many other examples of these other than just relationships, but I thought that this was quite funny. So this is the case here too. Since sodium is slightly positively charged, we call it a cation. And then again, chlorine, which is slightly negatively charged, it is called anion. And this completes our definition of the ionic bonds. This slide here provides a nice summary of the factors that we have covered for this type of bond. We are now ready to move on to the last type of bond that we will be looking at. The last type of bond that we will be discussing in this video is hydrogen bonds. And I have a definition for this too, but let's take a step backwards and consider why would we have a special type of bond for water? We remember this view of the Earth from our first chapter. We remember that water is essential for life. Much of the Earth is covered by water, and about 65 to 75% of you is water. And of course, we know that life evolved in water. It is for these reasons that when we go to seek life on other planets, we are looking for water or evidence of water. And this would make a really good question for your homework, wouldn't it? Why do we look for water or signs of water from other planets when we are looking for evidence of life? Just saying. So you remember this structural formula of water that we saw earlier. And we also noticed that water was what we called a polar molecule. You remember that polar meant that the electrons are shared unequally between the elements in question. And we remember that this was suggested by the fact that there were 3 atoms and they were not lined up on a straight line, but there was this kink, if you wish. So this fact that the hydrogen atoms and oxygen atom do not share electrons equally is what causes this. And here I have just colored the hydrogen atoms with yellow and the oxygen atom with green. It is still a water molecule. Because the shared electrons spend more time with the oxygen atom than hydrogen, the oxygen end of this molecule becomes slightly negative and the hydrogen ends become slightly positive. So that is our single water molecule. We notice that there are slight differences in the charges of different parts of this molecule, just as we discussed. And I have just edited the water molecule to look a little bit more like a space-filling model than the earlier structural model that we have been using. Now, I did scale down the size of this water molecule. And I added a bunch of other water molecules. Now we are starting to see something that is important for us, as for understanding what happens in the hydrogen bonds. And just remind yourself that opposites attract each other. Now we will notice that these water molecules are not arranged in a totally random manner. Instead, they are arranged so that the negative pole from one molecule is attracted to the positive pole in another molecule. This attraction that we will see is actually what the hydrogen bond is. And we will see that there are lots and lots of bonds here. One last thing that I do want to mention about hydrogen bonds is that hydrogen bonds are not very strong. So they are known as weak bonds. And this has an effect on some of the properties of the water. Now we have reviewed all three of our bonding types. You recall that covalent bonds were all about sharing electrons. Ionic bonds resulted from when one atom gave away and another atom gained electrons. And this caused a difference in their overall charges. And what I want to note here is that as a result, elements that bond with ionic bonding often form salts. See this figure here where negatives and positives are attracted to each other. And finally, we had a look of hydrogen bonds. This was a special type of weak bond between the water molecules due to the slight differing charges at the different ends of the water molecule. And that is where I will finish off with this video, and our last video for this module will pick up from right here where we left. We will be discussing what makes water so special that it is considered so essential for life. I hope to see you on that video. Until then, bye-bye.